Okay, so it will be a very short lecture today. Before we do more problems, I want to make a few comments about the inertia tensor. It won't take too long. Before we do that, one thing that I was surprised not to receive any questions about still has to do with the last problem we've seen, and I'm just going to quickly draw this, and has to do with the way we computed the angular momentum and the second law of Euler. So we picked this point Q, and the reference frame A was this guide that has a circular cut in it, and then this was C, and then we had the ground down here. And so we were looking at these two expressions, HQ in G. We know that it's H bar in G plus RQ minus R bar cross with mass of the C disk, velocity of Q in G minus velocity of the center of mass in G. And then Euler's second law tells me that ddt in G of HQ, so Q is a generic point, HQ in G is the moment of all forces with respect to that point we picked, plus RQ minus R bar cross with M, the acceleration of that point in the inertial reference frame. And we had the choice of Q, bless you, because the forces acting here, the reaction that is normal to the guide, and then the static force of friction, they would have no contribution to the moment if you pick Q. But then Q can be different things. It can be Q part of A and Q part of C. We know that the velocity of Q part of as seen belonging to A with respect to the ground is the same as the velocity of Q seen belonging to C as viewed by an observer with respect to the ground. That's the rolling condition, right? And we said, okay, for this we're going to stick x dot Ex in there, so it doesn't really matter which point you pick, if it's on A or C, right? But then we said, well, the acceleration of point Q seen as part of A with respect to the ground, I know that this is x double dot Ex because all points on that reference frame A are only translating, but this is not the same as the acceleration of Q as seen belonging to the disk now with respect to the ground. This is not true. And I think we agreed on that, because that's the instantaneous point of contact. This is the roll condition here that we're using, right? This is something that we defined. This means rolling. So we know we can do this, but we also know that we cannot do this, because those 2 points, Q on A and Q on C, are moving in a different way, are going to have a different velocity after this instant. And so the question that I'm posing to you, and I'm not going to give you the answer, you have to think about this, I strongly recommend that you think about this, is the following. Look at these two equations. This is the first one tells you how to basically move your angular momentum with respect to center of mass to another point Q, generic point. So here I don't see any difference if I pick Q on A or C. V bar is the same, M is the same, this is the same, everything is the same, the velocity as well, because that's a rolling condition. But then I go to this second equation. HQ will be the same. Doesn't matter if I pick Q on C or A, because that's what I just noticed there. And so this will be the same. This time derivative will be the same, no matter where Q is, on C or on A. MQ will be the same. This vector is the same. This is different. I just told you that that needs to be different. Otherwise, it's a hinge condition. It's not a rolling condition, right? Now, if I pick A, if I pick Q on A or C, this vector is going to be different. How is that possible? Everything is the same. HQ is the same. The left-hand side of this equation then will be the same. MQ will be the same. RQ minus R bar is the same. This, I'm telling you, is different. How is this working? How can it work? I'll leave this up to you. It does work. We know it works. But you need to show why. I strongly recommend that you go back home and you do your homework and maybe compute this vector here and see what's going on. Because you pick Q, but you need to tell me if Q is the point of contact between two objects that are rolling on each other. Point Q behaves in different ways depending on which object it belongs to. But things still work fine. So there is in principle a difference here. but I leave it up to you to show to yourself why this works just fine. And it's not a huge, complicated demonstration, but I was expecting this question. No one raised this question, but I did raise it to myself, and there is a very simple reason why things still work. So you can pick Q on A or C, and of course you're going to get the same equation. You need to get the equation of motion. It cannot change. If the variables are the same, you need to get the same equation, but why is everything the same, this is different, and still working? Do it. I recommend you try to figure it out. It's not a huge deal. But these are the things that you should be asking yourself. These are not just simple formulas where you pick a point, you stick the pieces inside, and you give up on understanding or asking yourself questions. Look at the formulas and say, oh wow, if I change Q, seen from as belonging to A or C, there is something different there. How is this still working? You should really ask yourself these questions. Because otherwise you're just opening the book, grabbing a formula, stick things in there, and you don't know what's going on. Okay? So do this as a homework. And then I want to leave a few minutes at the end of this short lecture for your reviews. You know, you can start leaving evaluations for your classes. It opened on Saturday. You have until the 24th. I hope it's clear how important it is to me, but it is important to every faculty and every department that you do that. The suggestion is that we do it in class, since basically maybe 10% of the class is here every time. I'll just put it on video that at the end of this lecture, please do the survey, because it is important. And I do use that information for next offerings. If you are enjoying classes and you're really understanding something in these classes, it is probably also because people before you gave feedback. So it is important. Okay, inertia tensor. So we defined it. I told you that we always go to the center of mass. Why do we need the inertia tensor? We need it to compute this vector, right? H bar with respect to inertia reference frame is equal to I bar of the rigid body R dotted with omega R n. So in every problem where we have rigid bodies and rotations involved, first thing we do is we compute the inertia tensor of the rigid body with respect to the center of mass. We need to pick some body fixed coordinate system and compute this, of course, if you want to have a projection at the end, a matrix. And then we have H, and we move on with our solutions. But I told you several times, there are some coordinate systems attached to the body that give you basically all the products of inertia going to 0. So let's comment a little more about that. First of all, this tensor here, just to refresh, is in general, before projecting it, it is given as I, what do you say? I'm sorry, it's a summation. It's a summation for I that goes from 1 to 3, another summation j that goes from 1 to 3 of I bar ij ei circle cross ej. So I actually already have picked a basis E1, E2, E3 here that is attached to the body R, right? So we pick some E1, E2, E3, and that's the expression for the inertia tensor, which in a matrix form, so when you write this projected in that basis, you can also say it's equal to I bar 1, 1, I bar 1, 2, I bar 1, 3, and then I 2, 1 bar. So these are all with respect to the center of mass, okay? We never do things with respect to other points because we have a way to move that H bar to another point if we need to. So why should we make our life any harder, right? 3, 2, and 3, 3. So in general, they're all real numbers that are non-zero. About this, we know that it's real and symmetric matrix, go back to the definition of all these components. They are integrals over the body of products of distances squared times masses, so they give you real numbers, and we demonstrated that these off-diagonal terms are equal to each other, so it's a symmetric matrix. Let's call this A. Let's just call this A. Okay. Now, being real and symmetric, first of all, means, what are the properties? Well, there is one that tells me that if I do the conjugate of the matrix and I transpose it, I get the matrix itself. There are no complex numbers there, so you can conjugate it as much as you want, which means changing the sign of your complex part. It's not going to change anything. So when you transpose that matrix, you get the matrix itself. Fine. So that's one property if you want. More important ones are the following, and this is why I asked you about linear algebra. It's a prerequisite. At this point, you should have some knowledge of linear algebra, but so I'm not going to demonstrate these things, but they should be known. A real symmetric matrix has real eigenvalues. Do we know what eigenvalues are? I assume we do. But let's just spell it out. So given a matrix A like that, an eigenvalue is in general a complex number that satisfies this expression here. So this is your eigenvalue. And this u vector is what is called the corresponding eigenvector, right? So if I have a matrix A which is real and symmetric, like the projection of the inertia tensor in a given coordinate system which is fixed to the body reference frame, its eigenvalues are going to be real. And then we have another property for the same type of matrix, the eigenvectors corresponding to I really can't write down here different eigenvalues. They are orthogonal to each other. Okay. So this is useful information because let's do the following. Well, first of all, these eigenvectors that you get use, you can always normalize them. So when you get an eigenvector, you normalize it, dividing it by its norm, and you make it such that its norm is 1. That's common practice. In real life, I mean, you solve for this. If you go to MATLAB, there is an expression that actually does it for you, finding the eigenvectors and eigenvalues. But let's do the following. If I define a vector or a collection of vectors, you want a matrix. And now I'm abusing the terminology. I'm calling vectors column vectors. Okay, so this is a matrix composed by column vectors. So if I organize all the eigenvectors like this, so these are column vectors, okay? And so this will look like a matrix. So defining these, let's see what I get when I do A times U. This will look like A U1, etc., A UN. But since that's the definition of eigenvector and eigenvalue, this is also equal to lambda 1 U1, etc., lambda n UN. Okay? There is another way I can write this, which is rewriting the u vector first and then defining a diagonal matrix with the lambdas on the diagonal. Agree? Doing nothing special. So that expression will end up being so from here I can rewrite that A U is equal to, let me call this matrix here capital lambda. Okay. I'm sure you've seen this stuff before. So it's U lambda. I take these and multiply times U transpose both sides. U transpose A U is equal to U transpose U lambda. What is U transpose U? It's the identity matrix because I get my eigenvalues, my eigenvectors. I told you usually you normalize them. So if you take that matrix of column vectors and you multiply times the transpose, you get ones and a bunch of zeros. So only ones on the diagonal. I hope that's clear. Okay. And so this is in the end telling me that U transpose A U is equal to lambda. And so that's another way of writing A, the matrix, the inertia matrix you started with, in a way that diagonalizes the matrix. And so these lambdas that you get are your moments of inertia with respect to the principal basis. So in other words, if you start from an inertia matrix, a generic one, you diagonalize it, you find its eigenvalues and corresponding eigenvectors, then you use those eigenvectors as the new basis. You are reprojecting the matrix, the initial one, in the new basis, and in the new basis your A, the new A, if you want, A prime, which is lambda now, will look like a diagonal matrix, lambda 1. Well, this is in general for any matrix, but here we're really looking at, 3 by 3 matrices. That's all we get for a rigid body. So those are your, what do we call these? These are the principal moments of inertia. As you can see, the products of inertia have gone. And the U1, U2, U3, you're going to have 3 of these, right? This is the principal, these are the principal axes of inertia. Okay? So, in real life, what happens is, so what I told you are in the books are basically these values here. For some specific shapes and mass distributions, usually uniform, you get in books the lambda 1, 2, and 3. And they tell you what are the axes of, the principal axis of inertia. This is a plural. Okay. So in real life, what you would do is you get your weird rigid body here. You should know and compute somehow the center of mass. Now, how is this done? You can do it experimentally in different ways, hanging this object in different positions and finding where that is, or by the sign. If you're actually creating something, building something, and you know very well the components, the mass distribution, the weight, etc., you can almost go into a CAD file and that computes the center of mass for you. That's what we've done for our spacecraft simulators in the lab, for example. And I'm pretty sure we have terrible estimates of the center of mass, but it still makes controllers work, so cannot be that bad. So somehow you find your center of mass, and then if the shape of the body is so obvious, you can try to draw the principal axis right away, because symmetry axes are principal axes of inertia. But in the other cases, you just pick some convenient initial body-fixed coordinate system. you will start applying torques about this axis and do experiments, and you know the torque you apply, you measure the angular velocities with gyroscopes or other means. So in other words, you can get an idea for the matrix of inertia in E. So you can get A, if you want actually this is the inertia tensor, right? This is the inertia tensor of this body projecting in this initial E1, E2, E3. Well, once you have this matrix, you diagonalize it, you find the 3 eigenvalues, and you find 3 vectors. These 3 vectors will be given, projected in this initial basis you had. So now you will have the U1, U2, and U3, whatever they are. So when you do the operation of finding the lambdas and the u's, you find the u's as projected in the initial basis, and then you switch to that. That's exactly what we've done before by doing UT, A, U. You're taking A, you diagonalize it, so you are reprojecting the inertia tensor in a new basis, U1, 2, and 3. So that's what I meant when I said, okay, these I don't know, we've done some problems. The typical is the disk. The axis that sticks out of this, or maybe if it's a cylinder, it's homogeneous. The symmetry axis is one of the principal axes of inertia, and then any on the perpendicular plane that are orthogonal to these are also other 2 axes of inertia, of principal axis of inertia. So that's what really happens. You have a rigid body, somehow you decide on an initial coordinate system attached to it, compute your matrix of inertia, then you diagonalize it, and you find the principal axis of inertia and the corresponding moments of inertia. This is done for spacecraft all the time, because the equations of motion, of course, they get simplified if you get rid of moments of products of inertia. They all go to 0. Things look much easier. And depending on how we do with solving more problems, the rest of this week and maybe Monday, I may show you something about what is done for spacecraft, but it's really not that much different from what we have seen. But for, in that field, we assume that you have everything done in this basis, because it's so much easier. Any questions on this? I thought I would spend a few words because we mentioned principal axis of inertia. We said that those things are in books. We said that somehow this matrix can have all the products of inertia going to 0, and that's how you do it. So if I gave you the matrix of inertia of a body in a generic coordinate system where those off-diagonal terms are non-zero, that's what you need to do. You need to find eigenvalues and eigenvectors. And you can find a more convenient reference frame. The obvious convenience is that when you do your H bar in N, it will look like, if this is how the tensor of inertia looks like, you will only have I, say, bar XX, EX, circle cross EX, plus I bar YY, EY, circle cross EY, plus I, Z bar EZ, circle cross EZ, and you stop right there. And then you dot this with whatever is your expression for the angular velocity. Otherwise, you would have 6 more terms in there. It's obviously nice to do it in this way. I think this really concludes what I wanted to do in terms of theory. I strongly invite you to think about what I told you before about that problem. We'll solve 2, 3 more problems, depending on how long it takes to solve one. So we have 3 more lectures left, right? Because I'm not counting the 22nd, because you have the test. So if you want, we can just continue solving problems. That's probably a good idea. If you don't want to, let me know. I may not teach next Monday and just be in my office waiting for questions. I don't know. You guys tell me. But the theory is done. You should really solve problems and think through them rather than just plug into the formulas. Questions, concerns, anything you want to discuss? We have time. Any problems you've been solving that are giving you a hard time? As you know, in chapter 6, there are the PDF I gave you, are there problems at the end? I think there are some problems, right? But there's no solutions. So a way to check on what you get, another nice exercise is, well, you come see me if you really struggle, but try to solve them without Lagrange's equations and compare what you get. You should get the same results, of course, right? No questions? Okay, so just to put it on video, now we do the survey. I invite you to do it, please. It's important. I just need to put it on video again before I shut this off. Thanks.